in our last lecture, we just finished the carry look ahead circuit, right? So I will continue from here, the parity generator and the checker. We already know what is the parity generator and the parity checker circuit. We need to send the bits with the data bits so that we can, at the receiving end, we can check whether my data is correct or not. In some cases, we can also correct it, right? So this is the parity generator and checker. So how we can create those parity generator and parity checker by using the logic gates. So we already know we have two different kind of parities. One is the even parity and another is the odd parity. In case of even parity means the number of ones including the parity should be even. If it is an odd parity, the number of ones including the odd parity, it should be odd. Okay. So there will be a data bits and as well as the parity bits. Okay. So how we can create this generator? Create the parity bit. So it's known as the parity generator. Parity generator. So this one for the even parity generator. That means we have to have even number of ones in the generator circuit, right? We have to generate even number of ones, including the data bits and the parity bits. So if we think about the 3-bit parity generators, and we consider this is an even parity generator, so this is the truth table for 3 bits input. And in the 4P, in the last column, we can see the parity bits. So this parity bits will be 1 when the input combination have even odd number of ones. For example, we have 0, 0, 1. In case of this one, 0, 1, 0. This is 1, 0, 0, and this is 1, 1, 1. In these 4 cases, we have odd number of ones in our database. So to make it even, the parity bit should be 1 for those 1, 2, 3, 4 mean-term cases. So output P equals to 1 when the total number of ones in the data bits are odd. So we have 4 different combinations that output P equals to 1. So we can make the Boolean expression from the truth table. This is the Boolean expression. So for this mean-term, it is A bar, B bar, C. This one A bar, B, C bar. This is A, B bar, C bar, and this is A, B, C. And if we just try to minimize the expression, then we can see this is nothing but an A XOR B XOR C. So that means we can generate an even parity circuit by using 2 XOR gate. 2 input XOR gate. It will give you a even parity generator circuit. Similarly, for the odd parity is nothing but the complement of the even parity, right? So we already see that we have 4 input combinations where we have the even parity P equals to 1, then other 4 will be P equals to 0, right? So this is 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So this is the Boolean expression. If we take from the truth table, if you get the Boolean expression and simplify it or minimize it, we can see this will be just X naught. A, X naught B, X naught C. So the output P column is the exact complement of the even parity generator. So we can implement this odd parity generator by adding one more NOT gate. So this is the even parity generator, this is the odd parity generator circuit. So we can easily construct the generator parity circuit. What about the parity checker? Parity checker usually check at the receiving side whether if it is there will be a agreement between the transmitter and the receiving side. There will be a agreement between the transmitter and the receiving side whether we are using the odd parity or even parity. If the transmitter side sends this odd parity, that means in the receiving side they will also check for the odd parity. That means total number of ones in the information will be odd number of ones. So this is the odd parity checker. That means we are supposed to transmit an odd number of ones. 1, 2, 3, 4, 5. So this is the transmitter, this is the parity bits, this is the data bits. In the receiving end, it's supposed to also receive odd number of ones. But due to the error, it is receiving even number of ones. 1, 2, 3, 4. One bit get flipped. So it will generate the error. So on the transmitter side, we are using the odd parity. So for the given data bit, the parity bit is 1 here. And at the receive side, the parity checker will check the receive code and find overall parity of the receive code is even. It's supposed to be odd, but it gets even. So it will generate the error. Excuse me, are you playing? If you want to play, you can go and play here. Okay? You have to set the priority. Yeah, thank you. So it's not meaning that I know you are reading, you can capture. This is very easy topics, but it's about the priority. In your life, sometimes the situation will come, you have to set the priority. That's it. I'm sorry. So this is the checker. So it will generate the error. Now in the event priority checker, same. So we have two even number of ones in the transmitting side. So even number of ones, 1, 2, 3, so 4. As we have already 4 ones, so we don't need to give any ones in the parity bit. So parity bit is 0. Now we are sending J data, and on the receiving end, 1 bit gets flipped, and when the checker will check, it will found 1, 2, 3, 4, 5, even odd number of ones. That means it will again generate the error. Okay. Simple. So if we don't have any error, that will create this no error. But we already saw that if we have a error, even number of errors, then the parity checker cannot detect those errors. That means if we have 2 bits here, 2 bits get flipped. That's why it cannot detect this error. So we already saw these things. This is the event parity checker and the odd parity checker. Now the question is how we can generate this circuit. How we can get this circuit. So for example, this is the example for the event parity checker. That means it will looking for the even number of ones at the receiving side. So here this is the input A, B, C is my data bit and P is my parity bit. So in total we have 4 bits. That means we have total 16 combinations. Okay. So as we are looking for the parity bit checker, that means even number of ones. So if we don't have even number of ones, then it will get an error generate and 1 to see that there is an error. For example, this one 0001, 0010, 0100. So here we have 2 ones, here we have 2 ones, here we have 2 ones, here we have 2 ones. So whenever there is a 2 or even number of ones, parity checker will not generate any error. It will generate 0. And whenever there is a odd number of ones, it will generate 1, right? It will generate 1. So if you get the Boolean expression for this table, then we will get that it is A XOR B XOR C XOR D. So by getting 3 to input XOR gate, we can generate a parity check circuit, even parity check circuit. So 2, 1, 2, 3, 3 to input parity XOR gate. So for the odd parity checker, it will be just X0. So we need to get another NOT gate in front of this. So this one. So this is for the odd parity checker. We should have the another NOT gate. So this is how we can actually generate, create the circuit for parity generator as well as parity checker. We need the parity generator in the transmitting side. We need the parity checker at the receiving side. So this is all we cannot finish last time from the previous lecture. Now we'll move to our today's one, that is, we'll discuss about today about the multiplexer and the demultiplexer. So a multiplexer, usually also known as MUX, in simple it is known as MUX, is a device that allows digital information from several users to be routed onto a single line for transmission over the line to a common destination. This is most common, most widely used applications, the MUX and the DMUX, because in the mobile telecommunication, we use TDM, time division multiplexing. We need to use this time division multiplexing because we have to use the frequency, and those frequency, the spectrum, we need to buy. We need to pay to the government for each and every frequency slot, and they are very expensive. That's why we need to use the time division multiplexing so that we can use that frequency very efficiently. So that means if we have one frequency channel, for example, here we have around 20%. If we want to use 2 or 3% using the same channel, for example, using the same AT&T Mobile or T-Mobile, so whenever you are connected to its nearest channel or nearest antenna, it will give you a dedicated frequency channel. But this frequency channel usually has something like that. So this channel, it can be again divided with 8 times slot. 1, 2, 3, 4, 5, 6, 7, 8 times slot. Whenever, that means each channel can use by 8 users at a time. Okay? If we don't have any user, if you have a 4 user, it will take more bandwidth. But whenever the user will increase, it can give it to 8 users at a time. So that means if you want to use only one frequency for one person, it is actually inefficient. To make it efficient, we need to make it efficient by using the time division multiplexing. Same way, we have to use the multiplexer. That means we are giving digital information from several sources to route it onto a single line for transmission over that line to a common destination. That means we need to connect from usually how the mobile communication connect. Usually we have the mobile station, our phone, it will connect to the nearest antenna tower. Then this tower will give it to the center, it is called BSC, something, a switching center. In the switching center, you have all the informations about your informations, about the caller information, the calling person information. Then they will check whether they are all the valid information, the number is valid, the account is valid. Then it will give it to the next stage, to the MSC, Master Switching Center. From the Master Switching Center, then it will try to find out what is the location of the person that we are calling. Then through another BSC, it will get that person. Once they got the person, a dedicated channel will be established between these two users. Okay? But whenever our voice or your data is going from BSC to BSC, so this is a common destination. After the switching center, then it will be again distributed. Then we use the demultiplexer. So this is how one of the applications. So it is also a combinational circuit, right? It is also a combinational circuit, and it has n inputs and only one output. It also has n selection lines. In the multiplexer, we have 3 things. One is the selection lines, another is the input lines, another is the data output lines. In the input lines, that means we have the data inputs, data. So, and we have the output, only one output. That means, depending on the combination of these selection lines, one of the data will be connected to the output. One of the data will be connected to the output. So if the m mux has n selection line, then the total number of inputs is equal to 2 to the power n. Okay? Or if the mux has n inputs, then the total number of selection lines is equal to log m to the base 2. So vice versa, we can select. So selection line, that means combination will decide which input will be available at the output. So here actually there will be a counter, a switching circuit here. The counter will, like this, will shift from T1, T2, T3, T4. Then one of the input will connected to the output, then next, then next, then next. Then it will be given like this. So if this is a counter or clock, then it will select like this. So at first T1, then T2, then T3, then T4, T5, T6, T7, T8, like this. So the time period, one of the, then it will come back again, then again from T1, T2, T3. So like this, it will give the input to the output line. So one input will connect at a time to the input, depending on the combination of the select line. So in general, there will be a different kind of mux. From the very beginning, the simple one is 2 into 1 mux. Okay? That means there will be 2 input and only 1 output. And to select any of these 2 input, we need just only one selection line. So this input are usually we known as data inputs. Data 0, D0, D1. So selection line will select whether D0 will be connected to the output or D1 will connect it to the output. Then we have 4 into 1 mux. That means we have 4 inputs and 1 outputs. And to select any of these inputs or data lines, we need how much? 2 selection lines, because 2 to the power 2 means 4, 0, 0, 0, 1, 1, 0, 1, 1. When we have 0, 0, D0 will connect it to output. When we have 0, 1, D1 will be connected. When 1, 0, D2 will connected, and 1, 1, D3 will be connected to the output. Then it will come back again. Simple. So, as I mentioned, so this is the 8 input marks. So we call it 2 into 1 marks, 4 into 1 marks, 8 into 1 marks. So the number of inputs to the output. So here we have the user that I mentioned already. So this marks used in analog and digital communication for time division multiplexing, where channel bandwidth is limited and need to share the resources with multiple users. So that's why we need this multiplexer. In time division, analog or digital communication, both cases. In analog communication means amplitude modulation or frequency modulation. Digital modulation means the PCM, PPM, PTM coding modulation, like those things. Okay. So this is the basic things. Now we need to construct this circuit, right? So to construct this circuit, the first step is we have to have the truth table. And then from the truth table, then we'll construct the Boolean expression. And from the Boolean expression, finally, we'll get our logic circuit. So this is the very basic steps to get the circuit. So this is the 2 into 1 marks. That means we have given the S, one selection line, 2 inputs, and 1 output. So when the selection line S equals to 0, data line D0 will be connected. And when the selection line S equals to 1, data line D1 will be connected. Now D0 can be 0 or 1. If it is 0, it will give you 0. If it is 1, it will give you 1. So this is the overall, but in short, this is the truth table. When S equals to 0, D0 will be connected to the Y. When S equals to 1, D1 connected to the Y. So from this truth table, we can have our Boolean expression Y equals to S bar D0 plus S plus D0. It's SOP, right? Sum of product form. So all of the things actually SOP. Mostly, right? It is also an SOP form. So when S equals to 0, output is connected to D0, data line D0. When S equals to 1, output is connected to D1 line. So from the truth table, we got this Boolean expression, and from this Boolean expression, we can just simply construct our logic circuit. So this is the logic circuit. In this logic circuit, we have 1 NOT gate, 2 AND gate, and 1 OR gate. Okay. And data inputs are given to the 2 inputs AND gate, and one is the data inputs, and another is the selection line input. One will be given directly, and another will be given to the complement form through a NOT gate. And then output of this 2 AND gate will be given to the 2 input OR gate. So SOP form. So this is the truth table. As I mentioned, we need to go through this truth table. This is the truth table for 4 into 1 marks. That means we have 4 inputs and only 1 output. So depending on the selection, any of the input will be connected to the output. 0, 0, 0, 1, 1, 0, 1, 1. When 0, 0, D0 will be connected. When 0, 1, D1 will be connected. 1, 0, for 1, 0, it will D2, and for 1, 1, D2 will be connected. So from the truth table, we can easily implement our Boolean expression, right? So Boolean expression is what? A bar, B bar, D. So S1 bar, S0 bar, D0. S1 bar, S0, D1, S1, S0 bar, D2, S1, S2, D3. So this is the Boolean expression. So to implement this Boolean expression, we need 2 NOT gate, 3 input AND gates, and 4 inputs OR gate. Right? So for this is the for 8 into 1 marks. That means we have 8 inputs, 1 output, and to that we have to have 2 to the power 3, which means 3 selection lines, right? 3 selection lines, S0, S1, and S2. And this is the truth table. It will go same as it is. So in this case, whenever we can increase the number of multiplexing, that means the number of AND gates with more number of inputs. For example, here we need 3 input AND gates and 4 inputs OR gate for 4 into 1 marks. For 8 into 1 marks, we require 5 input OR gates. So that means complexity will increase and the cost will increase. So we can actually implement the higher order marks by using the lower order marks. For example, this one. So for example, if we want to implement this 8 into 1 marks, we can also implement it by 4 into 1 marks. So in 8 into 1 marks, we have 8 inputs and 1 output. But in case of 4 into 1 marks, we have 4 inputs and 1 output. So that means to have 8 inputs, we should have 2 4 into 1 marks. 2 4 into 1 marks. And in case of 8 into 1 marks, we have 3 selection lines. But on the other hand, in case of 4 into 1 marks, we have only 2 selection lines. So how we can choose these selection lines? We'll choose the selection line starting from the LSB. Starting from LSB. So this is my 8 into 1 marks. This is my requirement. Actually, I want to have 8 inputs to connect to 1 output, right? So we should have these 8 inputs. So if we are starting from the selection LSB, the selection line S0 and S1 will be given to both of the 4 into 1 marks. Now, this 4 into 1 marks will give you 2 inputs, right? 2 4 into 1 marks will give you 2 inputs. And then these 2 inputs will be given to another 2 into 1 mask. Another 2 into 1 mask. And this 2 into 1 mask, that means it has required 1 selection line. So this MSB S2 will be connected to that selection line. To that selection line. So, do I have these? Okay. So if you want to choose any of the application, for example, anyone, so we have S3, S2, S1, right? S2, S1, S0. So if you choose, for example, 101, 101. So that means 101, that means 01 and 01 is giving here, right? 01 and 01. So whenever we have 01, that means D1 will be selected. Here 01 means D5 will be selected. So here we get D1 and D5 here. Now here S2. S2 is which one? S2 equals to 1. So as S2 equals to 1, that means this one will be selected. When this one is selected, D5 will be there. So we'll get 101 means D5. So we'll get the D5 connected. That means data line 5 will connect it to our output. Okay? Yes, sir.
Is this more efficient than this one?
No, not efficient. Yeah, efficiency in terms of complexity, because as I mentioned, if you increase 8 into 1 marks, that means the OR gate will have more inputs. AND gates will have more inputs. Then the complexity and the circuit complexity and the cost increases. So if you use 2 into 1 marks, the complexity will decrease and the cost will decrease. That is. But in terms of speed or that things, maybe. I'm not sure. I need to check. Because the speed depends on the AND gate, OR gate, its own propagation delay. So in terms of that, I need to check.
If the complexity is getting down, does the space also gets down?
Yeah. Inside the integrated circuit, of course, because we'll see in future that we'll design all these AND gate and OR gates. We are talking about this AND gate and OR gates, right? That is performing this logic. But this AND gate and OR gate actually we need to construct with some MOSFET, right?
I think
So
the space will not decrease, right?
Because it is data.
We increase the number of gates in this space when we compare it. Only 8%.
Only cost, I think. A space maybe because if we need lower MOSFET, because as I mentioned, we need to construct those AND gate or OR gates using the MOSFET. So if we can reduce the number of MOSFETs, then it will also decrease your space in the integrated circuit. So for example, whenever you use the IC in our lab, so we have the 4 into 1 marks, right, usually. So in the 4 into 1 marks means inside the 4 into 1 marks, this is the circuit we have. Do I have this circuit? So this is the circuit we have. So this circuit is have NOR gate and also the AND gate. So that means we have to implement these 4 AND gates with those MOSFET, right? Yeah. But still I will get more information and will get to you. Okay, where we are? No. So we can also, these are the options. We can actually implement anything. If you want to implement, if you don't want to use 4 into, here we are using 2 4 into 1 marks and 1 into 2 marks, right? Sorry, 2 into 1 marks. We can implement it by using all the 2 into 1 marks. Even make it lower. So 2 into 1 marks require only one selection line, right? So starting from the LSV, we will start give it to this L0 to all these 4 marks. Now to select any of the 4 outputs, we need another 4 into 1 marks. Because in 4 into 1 marks, there will be 4 inputs, right? To select those 4 inputs, we need another, the rest selection line will be given to here. Now from here, it will be select any of the 1 for 21 marks. Okay. So selection line as now is connected to all the every multiplexer. To select any of the 4 outputs, you require another 4 into multiplexer. To select any of these 4 inputs, selection line S1 and S2 is connected to 4 into 1 marks. This is how, yes sir.
Will we cover other forms of multiplexing besides time division, or just time division in this class?
Only this one.
Okay.
So this is the truth table of 8 into 1 mask using 2 into 1 mask. So here it is 3 level. This is level 1, 2 into 1 mask, 4, 2 into 1 mask, that it will be given to second level, 2 into 1 mask, and in the third level. So this one select any of these 2 output, this will select of any of these 2 output, and this one will select any of these 2 output. So this is how we can also implement by using 2 into 1 mask to implement a 60 into 1 mask. So this is for 16 into 1 multiplexer by using 4 into 1 multiplexer. That means, so we have 16 inputs. So to get all the 16 inputs, we should have 4 into 1 marks. And to select any of these 4 into 1 marks, we need another 4 into 1 marks, right? So by using 5 4 into 1 marks, we can actually implement 60 into 1 multiplexer circuit. Now, implementation of the Boolean function using multiplexer. That means we can actually implement any kind of Boolean function by using the multiplexer as well. So this is the logic circuit of 4 into 1 mask, right? We already saw before. This is the logic circuit of the 4 into 1 mask. And we have 4 into 1 mask, we have 2 selection lines, right? If you give the variable of the function these 2 selection line, then according to the variable, these 2 variable, we can actually get any of the minterms of this variable. So that means we have 2 variables, A and B, right? So we have the possible input means A bar, B bar, A bar, B, A, B bar, and A, B. So all the 4 minterms can be generated by this 4 into 1 mask. So here this is the Boolean function, this is the logic circuit of the 4 into 1 mask. So this is the apply the input variables to the selection line, we will all get all the minterms of the function. In this example, we will get all the 4 minterms for 2 variable function, and using this individual data line, we can now select the particular minterm. Which one you want? If you want A bar, B bar, or A bar, B, or A, B bar, or A, B, we can individually select from here. Then if you give it to the 4 inputs OR gate, it will give you the whole SOP form. So making the data lines either 0 or 1, we can select particular minterm. Okay? So here minterm is there. So it is 3 input AND gate. So here we have A bar, B bar, A bar, B, A, B bar, A, B. Now depending on the input, another input of AND gate, D0, D1, D2, and D3, we can select any of the minterms. If you want all the minterms, it will be 1, 1, 1. If you want 1, 0, 1, that means it will be given to the D5 minterms. So, for example, this is the function is given. So, and we already know whenever the function is given in this order, it is means it is the minterms, right? So minterms, which one is the minterm? 0, 2, 3, 7. 0, 2, 3, 7. So in this function, these 4 minterms will be high. These minterms will be high, 0, 2, 4, and 7. And all other will be, output will be 0. So if you give the, as this is a 3 variable functions, so we should have 3 selection lines. And we should have 3 selection lines where we have 8 into 1 marks. So we have to have 8 into 1 marks, and we have 3 selection lines. And in this selection line, we give this ABC my data, my variables. Now, which one we require at the output side? We require at the output side minterm 0, minterm 2, minterm 3, minterm 7. So minterm 0 to 7 will be connected to data line 0 to data line 7. That means data line 0, data line 2, data line 3, and data line 7 will be connected to high or 5 volt, and other rest of the data lines will be connected to the ground. Then it will perform with this operation. Okay. Okay. So here we already saw that we can implement, to implement a 3-variable function, we need 8 into 1 mask. It is also possible to implement this 3-variable function with lesser selection line. That means a Boolean function with an n variables can be implemented with a mask with n minus 1 selection line. So for 3-variable function can be implemented by using a 4 into 1 mask. Okay, by using also 4 into 1 mask. So during the implementation, starting from the MSB, the first n minus 1 variables are connected to the selection line, and the last variables are connected to the data lines. So here we have three variables A, B, and C. To implement these things, we need 8 into 1 mask, because we need S2, S1, S0. Now if you want to implement this 3 variables function by using 4 into 1 mask, that means we have now S1 and S0, right? S1 and S0. During the implementation, starting from the MSB, the first variable are connected the selection line. That means the variable, for example, this is A, this is B. Starting from MSB, this one will be given to the selection line. And then other variables will be given to the data lines, either in true form or in complement form. Either in true form or in complement form. Let's see. For example, the same function 0237, here we implement it by 8 into 1 mask, right? Now we want to implement this by using 4 into 1 mask. So as I mentioned that at first the variable from the MSB will be given to the selection line. Okay? So we have 3 variables here. So starting from the MSB, the variables A and B will be given to the selection line. Now the rest variable will be given, C will be given to the data lines. How we can select the C variables to the data lines? Let's see. So this is the truth table for 3 variables, 3 input variables, right? 0, 0, 0, 2, 1, 1, 1. And my main terms or my function is given this one, 0, 2, 3, 7. So these 2 variables A and B has a combination of 4, right? 0, 0, 0, 1, 1, 0, 1, 1. Each of these 2 variables again have a C variables which can be also 0 and 1, right? So here we have AB 0, 0, 0, 1, 1, 0, 1, 1. Now C variables can be either 0, 1, 0, 1, 0, 1, 0, 1. Depending on that, if you look at here, when my both AB variable is 0, 0, we already know. So if we have this one, we have this one, no. This is the S0, S1, right? AB. So this is data line 0, data line 1, data line 2, data line 3. When AB is 0, 0, it will be selected, right? When it is 0, 1, data line 1 will be selected. When 1, 0, data line 2 will be selected. When 1, 1, data line B3 will be selected. So whenever we have 0, 0, that means data line D0 is selected. Now D0 will be connected to what? So when C equals to 0, we can see according to this function f equals to 1. When C equals to 1, f equals to 0. Right? This is the min terms. This is the Boolean expression of the truth table of this. So it's saying that whenever A and B input is 0, 0, the function f is the complement of C. That means if you have make a complement, that means you have a C variable, then if you connect a NOT gate, and it give to the data line D0. Next, 0, 1. Wherever AB is 0, 1, then data line D1 will be selected. In case of this D1, when C equals to 1, it is 0, sorry, when C equals to 0, output function is 1. When C equals to 1, it also 1. That means, irrespective of the variable C, the function f is always 1. So that this data line D1 will be connected to high or 5 volt. It will always connected to 1. The next one is 1, 0. When A and B is 1, 0, then data line D2 will be selected, and here the function f and the variable C is connected like that. Whatever the variable C is, either 0 or 1, the function is always 0. That means data line D2 will be connected to the ground or 0 volt. And finally, we have 1, 1, data line D3 will be selected. And here we can see the function variable C is equal to the function. Whenever C is 0, function output is 0. Whenever C equals to 1, function is 1. That means C will be connected directly to the data line. So that means now by using 4 into 1 marks, it will also give you the same result. This is how we can use. So please try this one. I'm coming after my prayer. You can try this one. So for this function, this is the result. So you can match with your result. So we have midterms 1, 3, 6, 9, 12, 14, and 15 is 1. So we have to put 1 for those midterms. That function will be high for those midterms, right? Particular midterms. That is 1, 3, 6, 9, 12, 14, and 15. And these are the 4 variables A, B, C, D. So as this is 4 variables, it's supposed to have 4 selection line. But now we are using 3 selection line. That means 8 into 1 mask. So if you have the 1 mask A, B, C, 3 variables, you have to give A, B, C here, and D will be given to the data line, right? So depending on that, so if you look at here, when AB equals to 0, then depending on ABC equals to 0, depending on D, the function will be, when D equals to 0, function is 0, when D equals to 1, function is 1, so I equals to D. Or next one is saying, when D equals to 0, function is 0, when D equals to 1, function is 1, F equals to D. In this case, whatever the D, the function is always 0, so F should be correct 0. For this case, it is when D equals to 0, variable D equals to 0, function is 1, when D equals to 1, function is 0, that means complement. So D bar will be given to that data line, and here it is following the D, variable D, so F equals to D. In this case here, whatever the input variable D, the function is always 0, so F will be connected to the ground. Here, the function F is the complement of the variable D, so that's why this data bit will be connected, the F, D3, these 0, 1, 2, 3, 4, 5, 6, 7. D6 will be connected to complement of D, and then finally, whatever the variable is D, the function is always 1, so D7 will be connected to high. So this is how we can implement any Boolean expression by using the multiplexer circuit. Okay. Before going to that, I have another example here with me. For example, we have a circuit like this. It's giving one output function. It has 4 inputs, 4 data lines, I0, I1, I2, and I3. So for that we have 2 selection lines, S1 and S0. It also has another line. This is given, this to I0 and I0 is given to X. This I2 is given to Y. And from here it takes a NOT gate. Complement from is given to I3. This is also given to S1. And the S0 is given to Z. This is connected to another input. So this is 4 into 1 mask, right? 4 input, 1 output, 4 into 1 mask, 2 selection line. We have an enable input. You have to find out the expression, the function, Boolean expression of the 4:1 mask. You have to find out the Boolean expression for the 4:1 mask. So here enable input is an active high, that means it will work when the enable input will be high. So how we can implement these things? So first we can see that this I0 and I1 is equals to I0 and I1 is equals to X. I2 equals to Y. I3 equals to Y bar. Right? Then S1 is equals to again Y bar. S0 is equals to Z. And enable input is equals to Z bar. This is given. So what is the Boolean expression for 4:1 mask? We already saw the 4:1 mask Boolean expression. If we go back, this one, right? So we already have Y equals to S0 bar, S0 bar, D0, right? Plus S1 bar, S0, D1 plus S1, S0 bar, D2, then S1, S0, D3. So instead of D, we can put the I, right? We just put the I here. As this is I, we can put I0, I1, I2, I3. On top of that, we have an enable input. This mask will work when enable input is high, right? So we have to have an enable input. When enable input is 0, low, it will not give you any output. So this is the logic function. Now if you put the value here, what is S1? S1 is equals to Y, right? S1 equals to Y. We can put Y here, so Y bar, right? S1, sorry, S1 equals to Y bar. S1 equals to Y bar. So Y bar and bar will be Y. Then S0 equals to Z. So Z bar. I0 equals to X plus S1 bar, that means Y bar. So Y double bar Y, S0 equals to Z, I1 equals to X, S1 equals to Y bar, S0 equals to Z bar, and I2 equals to Y. Then S1, S0, S1 Y bar, S0 Z, and I3 is Y bar, right? Then enable input is Z bar. Here we have
Y Z bar X.
it will be Z bar, I think. That's fine? Everyone is okay with me? Y Z bar X, Y Z bar X, sorry, Y Z X, Y bar Z bar Y, so Y is Y. We are fine. Y, okay. So this Y bar will become 0.
0.
Right? It will become 0. Anything else we have?
X, first two terms, if you take Z.
So then if you multiply these two, if we multiply now, this term is only moving, right? So now we have X, Y, Z bar, dot Z bar, that means Z bar. Then X, Y, Z dot Z bar, then it will be also cancelled. Then this one is Y, this one is Y bar, Z bar. This one will also cancel. So anyway, we have only x, y, z. If I just remove this one,
From the first two terms, if you take
so if you just again x, y, z,
xy comma,
x, y, z bar, then z bar means 0, okay? The second one, x, y, z, x, y, z plus z bar, z and z bar will become 0, right? This is already moved, y got y bar, so this is also already 0. Then we have y bar, z, z bar, z and z bar also 0. So we have only x, y, z. So this is how also you can implement anything here. Okay. Before going to another example, at first again I go here. Switch is here on the light. It's too dark. Okay. Now we'll see by using this multiplexer, we can also implement any of the logic gates also. Okay, so we'll use the 2 into 1 marks. By using 2 into 1 marks, we can implement any of these logic gates as well. So this is 2 into 1 multiplexer. Usually we have inside this block, we have this circuit diagram for 2 into 1 mask, and this is the Boolean expression S bar D0 plus S D1, right? So if you want to implement a NOT gate, that means if you give an A, it will give you a complement of A. So how we can implement this 2 into 1 marks to get, how we can implement a NOT gate by using a S marks. So this is the complete Boolean function for 2 into 1 marks, right? So if you can see, we need A at the output, A bar. So if you give the variable to this selection line, and to the data line, if you select D1 equals to 0, D0 equals to 1, and D0 equals to D1 equals to 0, then if you put A bar 1 plus A0, so you give A bar. Simple. To implement an AND gate, so this is 2 into 1 marks, it is the same. Starting from the MSB, we will give the variable, first variable to the selection line. So A variable is given to selection line. Depending on the A variable, then we need to select the data lines, right? So this is the truth table. So A can be 0 or it can be 1. When A is 0, so if B equals to 0 or B equals to 1, we can see the function Y is following the B. That means this data line D0 will be connected to 0. When A equals to 1, now B can be 0 or 1, and the truth table, from the truth table we can see that function Y or output Y is following actually B. When B equals to 0, Y equals to 0, when B equals to 1, Y equals to 1. That means this data line D1 will be connected to B. That means first variable will be given here, the second variable will be given here, then it will work like a,
I think it's A, Y is equal to A.
which one?
It's not Y equal to 0. Because Y follows A.
So A is given, the MSB will be given to selection line, okay? And now we have to choose the data lines. So which data line will be connected to the variable B? That's the point. So here is the truth table. So we can see this Y will follow A, Y will follow B when 0. That means we need to select data line 0. So what is the condition of data line 0? Either it will be 0 or B, right? So if you look at here, when data line B equals to 0 or B equals to 1, whatever the input variable is, output always 0. So that means this data line will be connected to the ground. So data line connected to the ground, 0. And now when A equals to 1, then B is 0. When B equals to 0, Y equals to 0. When B equals to 1, Y equals to 1. That means this data line will be connected to B. So if you put same thing in the equation of the two input, what is the equation? S bar, can you help me? S bar D0 plus S D1, right? So S equals to my A, right? A bar dot 0, A bar. So it's AB. AND gate, right? Okay. So for the OR gate, we can also implement the OR gate same way. The variable A will be given to the selection line. Now we need to select the data line from the truth table. And from the truth table, we can see that when B equals to 0, Y equals to 0, when B equals to 1, Y equals to 1. That means this data line B0, because we are talking about 0, this data line B0 will be connected to B. When A equals to 1, then data line 1 will be selected. Now when B equals to 0, Y equals to 1, when B equals to 1, Y equals to 1. Whatever the variable B is, output is always 1. That means B1 will be connected to 1. So if you connect like this way, it will use as a OR gate. For this NOR gate, so this is the truth table of the, we already know what is the NOR gate. It is A bar B, A plus B whole bar. So this is the Boolean expression for 2 into 1 gate. And we need to put here A0 or D0, A1 or D1. So now when B equals to 0, Y equals to 1, when B equals to 1, Y equals to 0 is B bar. So that means this data line D0 will be connected to B bar. And for when B equals to 0, Y equals to 0, when B equals to 1, Y equals to 0. Whatever the input variable is, output is always 0. So we just connect this data line D1 to ground. Then it will work like a NOR gate. So this is the NOR gate. That means we can just give a NOR gate, or we can use another mask here. For the NAND gate, same, we can just construct this truth table, and from the truth table, we can implement this one. This is for the XOR gate. In XOR gate, it is more easy because it is Y equals to B and Y equals to B bar here. So this means A bar B plus A B bar. It will be simple. And XOR gate just will be the opposite one. So this is all about this. We can implement any of the logic gates by using the mask example. Okay. Now we'll move to the demask. As I mentioned that this mask and demask is actually implemented together in the communication system. In the transmitting side, we will use the multiplexer or mux. In the receiving side, we actually use the demultiplexer or called demux. In the transmitting side, we give any of the input is connected to the output. Then we transmit it. On the receiving side, there will be many inputs. Then we need to connect any of the input to single output. So it basically reverse of the multiplexing. It takes digital information from one line and distribute to a given number of output lines. It is also known as data distributor. Data distributor. If I go to this picture, this one. So in the mux, we actually gather all the information, give it to the single line. And now here at the input in the switching center, as I mentioned, when you give the power to the MSC, to the BSC will take switching. Then it will give to the dedicated line. Why it is supposed to go? It can be given to person 1 or it can be given to person number n, 1 to n. So this is the distributor. It will take one input and this input can be connect any of this output line. So this is demux. So it is, that's why it is also known as data distributor. So here also multiplexer, we have selection lines, we have n number of inputs, we have one output. Here it is opposite, we have only one input, number of selection lines and number of output lines. Depending on the combination of the selection lines, the input will be connected any of the output. Okay? As I mentioned, to select a specific output, it has several selection lines. Depending on the input at selection line, the input is connected to a specific output line. Number of selection lines are log m to the base 2. With n selection lines, we can distinguish to the power n different outputs. Okay. So this is, we can have the symbol like this one, also like that one, and in short, we call it demux. Okay. This demux circuit actually can be implemented by a decoder circuit. In the next class, we'll talk about this encoder and decoder. But here, I will give just small idea of this decoder circuit. In the decoder circuit, we have n number of inputs and n number of outputs. N number of inputs and n number of outputs in the decoder circuit. And in the decoder circuit, we also have an input called enable input. So, excuse me. So in the DMUX, we have one input and several selection lines. So that means as DMUX have one input and in the decoder we have one enable input, that's why this input will be given to this enable line. In case of, if you want to use the decoder as a DMUX, you can give the input to the enable of the decoder. And enable input of the decoder circuit will be given to the selection line. Okay. So logic circuit of the decoder is very similar to the multiplexer. A little change in the decoder circuit, it can be used as the demultiplexer. That's why if you have the decoder IC, most of the cases the decoder IC also mention that slash demultiplexer because that it can be used both purpose. Connect to the input of the DMUX to the enable input. So you have to connect the input of the DMUX to the enable input and connect the selection line of DMUX to the input of the encoder circuit. So this is the decoder circuit, 3 to 8 line decoder. So it has 3 inputs, 1 enable output, and so 2 to 3 means it has 0 to 7 or 8 outputs. And this is the logic circuit of the 3 to 8 decoder circuit. So you can see here we require around 8 AND gates of 4 inputs each, and we also require 3 NOT gate. So by using this 3 NOT gate and this 8 AND gates, we can actually have all the midterms, right? We should have all the midterms of ABC variable, of 3 variables. Okay. So the output will be high, only 1 midterms. Depending on the combination of ABC, only 1 output will get high at a time. Only 1 output will get high. This is the decoder circuit. So if we want to apply this DMUX using the 3 decoder, we can have the same information. Our input signal or data will be connected to this enable input, and the selection line will be given to the 3 inputs of the decoder circuit. And depending on the input combination, this input signal will be connected to any of the output line. This is DMUX, right? One to many. So we have one input line. It's supposed to be connected when it is 0, 0, 0. This I1 will be connected to D0. When selection line is 1, 0, 1, it will connect it to D5. When it is 1, 1, 1, I will connect it to D7. So this is the 1 into 8 demultiplexer circuit as I mentioned. So this is the selection input, this is input of the I or the information of the data. So depending on this selection input, the data will be connected with any of the output circuit. And this is the truth table for that one, as I mentioned. So when 0, 0, 0, D0 will be connected to the input. When 1, 0, 0, D4 will be connected. When 1, 0, 1, D5 will be connected. When 1, 1, 1, D7 will be connected. So we can give the input to any of the output. So as mask, you will have also 1 into 2 mask, 1 into 4, sorry, 1 into 2 DMUX, 1 into 4 DMUX, 1 into 8 DMUX. This is the truth table and the logic circuit for 1 into 4 DMUX. Here we require 4 AND gate with 3 inputs each. And this is the truth table. So when D0, 0, D0 will be connected. When 0, 1, D1 will be connected. When 1, 0, D2 will be connected. When 1, 1, D3 will be connected. So the output will be connected either D0 or D1 or D2 or D3, depending on the selection input of the selection inputs. So this is the logic circuit of 1 into 8 demultiplexer. So we can see from the circuit, if the number of DMUX increases, then the input to the AND gate also increases. Here we require 4 input AND gates. So that means again the complexity will increase and the cost will increase. So we can make it or implement it by using the smaller DMUX circuit. So we can implement 1 is to 16 DMUX by using 1 to 8 DMUX. Similar way, we have to select those selection line. So starting from the LSB, the first three selection lines are connected to the both demarcs because we are trying to establish a 1 into 16 demarcs. To implement a 1 is to 16 demarcs, we have to have 16 different combinations. That means 2 to the power 4. So we should have 4 selection lines. Starting from the, now we are to implement it by using 1 into 8 demarcs, right? In case of 1 into 8 demarcs, we should have 3 selection lines. So starting from the LSB, the S0, S1 and S2 will be given to both 8 into 1 mask. Then to choose any of the demarcs, we have to have another 1 into 2 demarcs. In case of 1 into 2 demarcs, we need just one selection line. The LSB S3 will be given to here. So when it is 0, this one will be input will be connected to upper demarcs. When it will be 1, the lower demarcs will be selected. And depending on this S0, S1 and S2 selection line, any of the output will be selected or will be connected to the input. So this is how we can also implement 1 into 16 demarcs by using 1 to 8 demarcs. We can again implement it by using 1 to 4 demarcs. So in case of 1 to 4 demarcs, that means we need now 1, 2, 3, 4, 5 demarc circuit. In case of 1 to 4 demarcs, we have to have 2 selection lines for each. So starting from the LSB, S0 and S1 will be given to each of these 4 demarcs. Now to choose any of these 4 demarcs, we need another 1 to 4 demarcs. Here we will have the rest, S2 and S3 will be given. Here S0, S1, here S2, S3. So depending on the selection line, any of the demarcs will be selected. Then depending on this selection line, any of the output will be connected to the input. We can use the logic function to implement the logic function these demarcs as well. One of the most common application is we have a full adder circuit, right? In the full adder circuit, this is a 3 input and 2 output. In the output, we have sum and carry. We can implement this full adder circuit by using a demarc circuit. In the decoder also, we have 3 inputs, right? And we have 8 outputs. So this is the full adder circuit. And we can implement a full adder circuit by using a decoder circuit, 3 to decoder circuit. And 3 to decoder circuit actually we can use as a demarcs as well, right? We can use as a demarcs as well. So this is the truth table for the full adder circuit. We already know we have carry and we also sum. We have some output will be high for 4 different midterms, 001, 010, and 100, 111. On the other hand, carry output is high for another 4 different midterms, which is 011, 101, 110, 110. So depending on this selection line or input, we can actually choose any of the output, right? And we can give the input to here. So if you connect this data line, this is the demarcs, the selection line is A, B, C in carry, and we have this input line, right? This is my information line or data line. If you just connect this data line to high, then depending on the input combination, this high will be connected to any of the output. Now for the sum output, we need high for M2, sorry, M1, M2, M4, M7. So D1, D2, D4, D7 is connected to the OR gate. For the carry output, we need high for M3, M5, M6, and M7. So if you connect M5, 6, 7, and M3 to the another OR gate, then these two output of this two OR gate will give you sum and carry. So by using a 3 to 8 decoder or 1 to 8 demarcs, and with a 2 OR gate, we can implement a full adder circuit. Then another application is we can implement by a parity generator circuit by using the demarcs. So this one for even parity. So we already know the parity bit will be 1 when there is odd number of ones in the data bits, right? So this is 3 variables function. So here the parity bit will be 1 when there is odd number of ones for this case, for this case, for this case, and for this case. For 4 different midterms, the parity bit will be high, which is M1, M3, M4 and M7. So we need to connect these 4 minterms to the OR gate. That means if you give the 3 variables to the 3 selection lines and the input signal is connected to the high, then if you just take these 4 minterms and give it to the OR gate, 4 input OR gates, this circuit will actually act like a parity generator, an even parity generator. So if you want to make the OR parity generator, you have to take the other 4 variables, other 4 minterms. So this will work like a even parity generator. So this is the function. Now I have another example and then we finish. The circuit is given like this. Same. We have variable I0, I1, I3, input lines, data lines. This is the selection line S0, S1. So we give the input AB here, A and B here. Then we need the rest of variables here. This is C, and this is I2, D is given here, and another variable is given a function of minterms. Find the Boolean function using this logic circuit. You have to find a Boolean function. So it's a 4:1 mask. So it has 2 selection line, 4 inputs. So it's a 4:1 mask. 4 input, 1 output, right? And for the 4 input, we have 2 selection lines. So if you write down the function for 4 inputs, we already have function which is S1 bar, S0 bar, I0, S1 bar, S0, I2, S1, S0 bar, I3, and finally S1, S0, I4. Now you just put the value here. So S1 is A. So this is A bar. This is S1, this is S0. S0 is B. I0 is, which one is I0? I0 is C. Then this one, S1 bar. S1 bar is A bar. Then S0. S0 is B. Sorry, this one will be B bar. A bar, B bar. A bar, B. Then I2 equals to C bar. Then S1 A bar B. And then I3. I3 equals to, what is I3? C bar, B bar, right? I3 equals to C bar. There is a bubble, sorry.
I think you skipped I1.
Sorry.
I think you went I1. It should be I1, I2, I3.
I0, I1,
I.
yeah, I'm sorry. I1, thank you. I2, I3, yeah. So A bar, B bar, C, A bar, B, this one.
That's supposed to be D, not C.
Sorry, I'm sorry.
That's
This is
when,
I1.
Yeah, when.
I1 is D. Thank you. And this I2. I2 equals to C bar, right? A bar, C bar. And finally, we have A, B, and
C plus.
C bar, D bar. Now we can, anything mistake again? A bar, B bar, C, A bar, B, D, A, B bar, C bar, A, B, C bar, D bar. Now we can minimize this expression. So this is a non-canonical SOP form, right? Because we have 4 variables, but all the terms don't have the 4 variables here, right? So we already know how to make from non-canonical to canonical by shorthand method, or we can use the K-map. So if I use the K-map, so it's a 4 variable. So here we have AB, here we have CD, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, right? So first one is A bar, B bar, C. So in this column, this is A bar, B bar, and C means C is not changing this one. Which one C is not changing? 0, 0, right? C
It's 1, so it's the
1,
last
1. So this one, right? These two. Then second midterm is A bar, B, D. So A bar, B, this one is fine. Then D, right?
Second
So
and
D is
third.
not changing. Which one? Second and third. Then third midterm is A, D bar, C bar. A, D bar, this one.
C.
And
The
then C
first
bar,
two.
the first two,
Yes.
right?
Yes.
First two. And finally, A, B, C, D bar. This one A, B. And C bar, D bar
First one.
will be only this one. So here, from here, we can say this is the function of midterms. This one. So this is 0, 1, 2, 3, 4, 5, 6, 7,
Down.
8, 9, 10, 11, 12, 13, 14, 15. So we can write down 2, 3, 5, 7, 8, 9, 12. So in both ways we can implement it. Maybe if the function will be given, we can implement with the circuit, or the circuit will be given, we can find out the function. Thank you so much.